Hello, my friends. Welcome to Lesson 3 of Unit 5. We're going to be talking today about the concept of half-life and how that allows us to radioactively date the ages of certain events, even events that occurred thousands, millions, or even billions of years ago. Half-life is defined as the amount of time it takes for half of a parent isotope to decay into its daughter isotope. So in this image here, you can see that if we started with a sample, in this case 20 milligrams of a radioactive isotope, this is iodine-131. If we started with 20 milligrams, after one half-life, which would be 10 milligrams, half of it would have decayed. So you can see that it is now turned into the daughter isotope, which is xenon-131. This means, if you remember from lesson 2, this means that this is an example of a beta decay. You can see that the atomic number has increased from 53 to 54. One of the things that students sometimes find confusing is they think to themselves, okay, well then if we do one half and then we lose half, then after two half-lives there'll be none left. Because if you take away half from half, you get 0. But that's not what's happening here. After the first half-life, half is gone, but then in the second half-life, half of that half is lost. Okay, so in other words, a quarter gets lost. So now we're down to just a quarter, and we have 3/4 of the daughter isotope. And then in the next half-life, half of that quarter gets lost, 1/8. And so it goes downwards, 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 okay? Always losing half and half and half. Now, theoretically, of course, that number never gets to 0 because you just keep dividing it by bigger and bigger numbers. The fraction keeps getting smaller and smaller and smaller. But in reality, you get to a point where you're left with one atom, and then once that one atom decays, there's none left. So there is a point at which the parent isotope is completely decayed into the daughter isotope, and the process has stopped. So half-life is simply the amount of time it takes for half of the parent isotope to decay into the daughter isotope. If we were to do a graph of this, it would look like this. So let's start by filling in our table. Now, here we're keeping track of half-lives. Always really important when we get to doing the calculations of this, you'll see you always start at 0. You have to start at 0. If you start at 1 here, you'll be wrong by one half-life every time. So make sure you start at 0. Now in terms of the amount, let's do this a couple ways. Let's do it as a percentage. Okay, so 100% or everything. And let's also do it in a fraction. Okay, so let's do 1. Right. Remember, 1/1 is the same as 100%. After one half-life, 50% of 100, which is 50, will go. So you'll be left with 50%. Okay. And what will happen is the fraction will change from 1/2 to, or I should say 1/1 to 1/2, half. Second half-life, you lose half of 50%. Half of 50% is 25. And you go from 1/2 to 1/4. What you should see here is that every time we move up one half-life, the bottom number of the fraction here increases by 2. Third half-life, half of 25, which is 12.5. 1/8. Fourth half-life, half of 12.5, which is, let's call it 6.25. 1/16, and then half of 6.25, let's round it up, let's make it 3.13. And that's the same as 1/32. Now, if you don't believe me, you can take your calculator out and you can divide 1 by 4 or an 8 and so on, and you'll get these same numbers. Okay, so now let's turn this into a graph. Here we have a graph with the amount of the parent isotope remaining on the vertical axis from 100% at the top to 0 at the origin. And then on the horizontal axis, the x-axis, we have 0 up to 5 half-lives. Now, we don't know how long the half-lives are. It's not important in this case. The first step, the first data point here is 0 and 100, which is right there. And then one half-life we're at 5, 2 half-lives, we're at 25. Sorry, it keeps doing that because it thinks I'm trying to select the screen. 3 half-lives, 12 and a half, so that's about there. And then 4 half-lives, 6.25, let's call it that. And then 3, let's say there. Okay, now if we draw lines, oops, for some reason I lost my first data point. We draw straight lines here, as we should do on a line graph. Not perfect, but you can get the point here. What you see is this curving shape. And this is often called a decay curve for this reason, because it curves down towards 0. All right. That is typical for all examples of radioactive decay, where you get this curving shape approaching 0 and always moving with each half-life down by half. Okay. If you go to data page 6, you will see that I have 6 different parent and daughter isotope pairs. That's the term here. They're called isotope pairs. And I've also specified in years what their half-lives are. So I could use any one of these parent and daughter isotope pairs, and you can look up the half-life here. Just a quick thing to say about half-lives. Half-lives vary greatly from very tiny amounts of time, way less than a second, all the way up to, as you can see here, many billions of years. This particular isotope pair, rubidium-87 and strontium-87, we estimate the half-life to be 47 billion years, which is far, far longer than even the age of the universe. So we haven't even seen a whole half-life of rubidium-87, strontium-87 yet, but we have, through careful calculations, estimated that that is its half-life. So as you can see, we can date things going back billions of years, and again, we'll talk about dating in just a moment. One thing to keep in mind here, and this is something that students often forget about because they're so focused on the parent isotope, is that as the amount of the parent isotope decreases, the amount of the daughter isotope increases. So let's say this is uranium-235. At 0, we have 100%. By 1 half-life, half of these uraniums have decayed into the daughter isotope, which is lead. And then by 2 half-lives, half of that half, and then by 3, half of that half of that half, and you can see that the amount of lead gets bigger and bigger and bigger. So here at 1 half-life it's 50%, and then it's 75, and so on. It continues to increase until eventually it's all daughter isotope and the parent isotope is gone. To put it into a graph like this, you can see this effect again, where the blue shaded area represents how much of the parent there is, and the gray shaded area represents how much of the daughter there is. You can see that the amount of the daughter isotope steadily increases, whereas the amount of the parent isotope steadily decreases as you move from half-life to half-life to half-life. Let's talk about a couple of different applications for this, and then we'll look at how we can actually calculate these problems. The first of these is what's called carbon-14, or carbon dating as it's often called. This isotope pair is an isotope pair which has a fairly short half-life, 5,730 years to be exact. The way that this works is you have radiation bombarding the atmosphere, and it converts nitrogen into carbon. Carbon-14 to be precise. Carbon-14 is very rare because it's radioactive, but it is present in sufficient quantities that it is picked up by plants, and it's picked up by plants when they photosynthesize. If you don't know what photosynthesis is, this is the process where plants pick up carbon dioxide from the atmosphere and they use it to build their bodies. So the bodies of plants accumulate carbon-14. Organisms that eat plants, like ourselves or sheep, will pick up the carbon when we eat the plants. So living organisms on Earth have a certain amount of carbon-14 in them, and that amount is replenished throughout their life as they continue to eat and feed. But when they stop eating, when they die, the amount of carbon-14 does not get increased anymore, and it starts to decay, starts to decrease. So carbon-14 allows you to determine the age of an organism since it died. It can't tell you how long it lived. It can only tell you how long it's been since it stopped eating, since it stopped picking up carbon-14. And because it has such a short half-life, 5,730 years, it only really lasts for 3 or 4 half-lives in the environment. And that means that you can date organic material, bones, teeth, plant residues, and things like that, going back a few thousand years. Now, even though it's limited in its age, it has been very, very useful for us. We've been able to date human skeletons and other remains that are fairly recent. It allows us to, for example, date cave paintings, which were made fairly recently because they're made with charcoal, which is produced from wood. So carbon dating is a really useful tool, allowing us to date the age of organic remains within the last few thousand years. Let's look at another isotope pair and another form of radioactive dating. This is the potassium-40 clock, as it's often called, which is the isotope pair potassium-40, argon-40. In this case, it is a similar process whereby molten rock, liquid rock inside of the Earth is picking up potassium-40. As long as it remains liquid, it continues to absorb potassium-40 at a fairly steady rate. But when that rock is ejected out of a volcano, for example, as ash or lava or some other form of volcanic rock, the amount of potassium-40 stops increasing and it begins to decay. So you can, the analogy here is you start the stopwatch at that point when the rock cools and forms what we would think of as a rock, hardens and cools, it begins to count. And as it decays from potassium-40 to argon-40 over many millions of years, you can take a sample of rock, as long as it's volcanic, as long as it's a kind of volcanic ash or some other volcanic rock, and it'll tell you how long it's been since that rock cooled off. Again, it doesn't tell you the age of the rock, it doesn't tell you how long it was waiting to cool inside the volcano, but it tells you how long it's been since that volcanic rock formed. This has been a very incredibly useful tool in geology, where geologists, the people that study rocks, are very interested in how old those rocks are, and you can use the potassium clock to date things that are nearby. So for example, if you have an ash layer on top of some fossils, it tells you pretty close how old those fossils are. Okay. So radioactive dating of this kind is very, very useful, and it's been applied to a huge variety of different scientific tools. It's very accurate, very precise, and very, very important. We want to be able to solve problems of this kind. So let's talk about how we can do this. There are many ways to solve half-life problems that are mathematical, but the method that I prefer to teach is not mathematical. It involves building a table like this that has 3 columns. The first column is the half-lives. Okay. The second column is the amount of time, and this could be years, it could be seconds, it depends how long the half-life is. And then the amount. And we could measure this in percentages, we could measure it in mass, we could measure it in all kinds of different ways, but that depends on what you've got. So the way that we do this is we have a problem or a graph or some sort of question that gives us information, and we fill in the parts that we know. So let's say, for example, we know the half-life. So we know that 3 half-lives have taken place, so we count up, starting always at 0, 0, 1, 2, 3. So we've done 3 half-lives here. And then to count up in time, we start at 0, always. Okay, really important. Sometimes students will put 1 half-life worth of time there, but you can't. You have to start at 0. And then you put in 1 half-life worth of time. Could be a second, could be several million years. 2 half-lives worth of time. 3 half-lives worth of time. And then you can use that information to figure out the amount. So the amount will start at 100%, as we know. it will then go to 50, 25, 12 and a half, and so on. Okay, or it could start as a mass, like 50 grams, 25 grams, 12 and a half grams, and so on. So if we know one of, or I should say two of these two things, we can figure out the third. So if we know what time and the amount are, we can figure out how many half-lives there's been. If we know how many half-lives and how much time there's been, we can figure out how much of the amount remains, and so forth. As always, it's one thing to talk about it, it's another thing to actually do it. So let's practice one. Here's our problem. If 50 grams of carbon-14 were present in a sample of bone, state how many grams would be left after 1,000, or I should say 17,000, comma there, 190 years. Now, if you go to your data page 6, you will see that the half-life of carbon-14 is 5,730 years. Okay, I'm not going to show it to you. You can do that yourself if you're curious, but take my word for it, that's how long it is. So what do we know from this problem? Well, we know how much it started with, so we know the beginning amount, and we know the time. Okay, and that means that we can solve for the half-life, and then we can determine how much amount remains. So let's start by building our table. Half-life, time, and amount. By the way, the order of these columns isn't important. I just do it in this way whenever I do it. It just makes sense for me to put half-life first. And then I'm going to draw some lines down like this to separate my columns, and I usually draw a line like that just to make it neat. Now we're going to start here at 0 and 0, and we're going to make sure that the amount is 50 grams. Okay, you have to start at 100%. Now, how do we know how much the amount is? Well, we have to solve the half-life and time columns first, and then we'll be able to solve for the amount. So we know that the final time, the time that we're interested in figuring out the amount, is 17,190 years. So let's go up to one half-life. One half-life is 5,730 years, so let's write that. Two half-lives is going to be 5,730 plus 5,730, or, in other words, 5,730 times 2. Either one of those is correct. Now I've got a calculator here. I'm going to do that quickly, and you can do it on your own. 5,730 times 2 is 11,460 years. Okay, we're not at the total yet. Notice that we need to get to 17,190. Let's go up to 3 half-lives. If we add another 5,730 to this total, or in other words, if we multiply 5,730 times 3 for 3 half-lives, we get a total of, 17,190 years. So that's our total. We've reached the amount that we need. Now all we need to do, the amount of time I should say, now all we need to do is figure out how much the amount of the radioactive parent isotope has changed. So if we start at 100%, which is 50, one half-life later, half of that 50 will be gone. So that will leave us with 25. I did that in my head, but if you need to do that, what you would do is take your calculator and divide 50 by 2, or multiply it by 1/2. 50 divided by 2 is 25. Now we need to go up to 2 half-lives. 2 half-lives would divide that total, 25 again. Half of 25, 25 divided by 2 is 12.5. Okay, we're not quite finished yet. We need to go up to 3 half-lives. So we're going to take 12.5, and we're going to divide that by 2, and that gives us 6.25 grams. Okay? So what we've done is we've used the number of half-lives and the time, which we got from the question, to solve the third thing that we didn't know, which was the amount. Now, with all these questions, we need to finish by answering the question. And the question says, how many grams will be left after 17,190 years? So our answer is going to be 6.25 grams would be left after 17,190 years. And that's our finished problem. Now, a couple things to remind you of before you try some of these on your own. Please make sure that you are starting at 0 here and at 100% for the amount. Really important. Make sure that every time you go up one half-life, you're adding another half-life worth of time to the total amount of time. Okay? So in other words, the half-life times 1, half-life times 2, half-life times 3, just as we did here. Okay? And then finally, make sure that every time you go up one half-life, you're reducing the amount, whatever it's measured in this case it's grams, it's mass. Make sure you're reducing the amount by half. Sometimes students will double it every time, but that's the opposite process that's happening. Okay. Now, sometimes these problems, as you'll see when you look at the examples, sometimes they'll give you the final amount. Let's say it started by saying after 17,190 years, you had 6.25 grams remaining. What you do in this case is you work backwards and you double it, going up the table. Okay, but that's something you can deal with when you come to it. Make sure that when you are moving up from one half-life to the next, increasing in time, that you are reducing the amount by half. Okay? If you haven't done so already, please head to the key, fill in the notes, lesson 5.3, and then you will see that in practice 5.3 are a series of half-life problems. There's some tables to fill in. There's some word problems like the one that we just did. Make sure that you are showing me your work. The work in this case is the table showing half-life, time, and the amount. And make sure that you are correcting your answers from the key. Not marking, but correcting them to make sure that you're doing this properly. And if you don't know what's going on with a question, make sure you make a note of it so that you can ask me in class. Thank you very much. Talk to you soon. Bye-bye.